This is Geometry, Chapter 10, Section 7, in which we will study special segments in a circle. Last time around we talked about secant lines and tangent lines and intersecting all over the place. And we figured out things about angles. In this lesson, we're going to be talking about not the angles, but the actual lengths of the segments themselves. Whenever we have two chords intersecting, and chords are just parts of secants, they're just the part that's on the inside of the circle. Whenever we have chords intersecting, the chords cut themselves into two parts. They're not necessarily congruent parts. They could be. There's no law against it, but they don't have to be congruent. Okay. The two segments that each chord makes are called chord segments. So AB is a chord segment, AC, AD, and AE. Those are all chord segments. And what our first theorem of this lesson tells us is that the product of the lengths of those segments is equal. So what they're telling me is AB times AD is equal to AC times AE. Okay, it's really all about similar triangles. If we connected BE and we connected CD, these two triangles would be similar. Then we could write ratios from the definition of similar triangles and then cross multiply to get this expression, if you happen to need that at some point. So let's do a few of these where we're working with these chord segments. We'll start with a simpler case. We have the four chord segments. The theorem says that the 4 times the 15 will be equal to 6 times x. All right. 4 times 15 is 60. Divided by the 6 gives us that x is 10. This is another one of those cases where you can't always trust your lying eyes. You might think, well, my goodness, that can't be 10. If that's 15, that's a little short for that or some such. But don't trust your lying eyes. Just trust the arithmetic. Or in the case of the next problem, the algebra. Okay. The same theory works. Okay. This piece times this one is equal to the x plus 2 piece times the x plus 6 piece. Well, now it's a simple algebra problem. We need to distribute things out. I'm going to subtract x squared from both sides and they cancel, which makes life a lot easier. We'll subtract the 8x over and we'll get 4x equal to 12, which tells me that x is 3. Okay. That was an intersection on the inside of the circle. Okay. The other intersections we're going to be looking at will be outside the circles, which means we need to get a few more terms. Right? A secant segment is part of a secant line. It starts at the circle, goes through, and comes out the other side. Okay. AC here is a secant segment. And it has two parts to it. It has an internal part and an external part. Okay. AB is obviously the internal. BC is obviously external. Now, this is useful with the secant segments theorem. We need to understand where these parts are. If you have two secants intersecting outside the circle, then the product of the whole segment times the external part is equal to the whole segment times the external part. PS, the whole thing, times PT, the outside, equals PR, the whole thing, times PQ, the outside. Let's apply this idea to a couple of problems. Okay. We have two secant segments. The theorem says the whole segment here, so x plus 9, times the outside part, which is x, equals the whole segment, 4 plus 5 is 9, times the outside part. Okay. Distribute. Let's just subtract the 36 over. Now we can factor. When we factor that, we get x plus 12 times x minus 3. So x equals negative 12, or x equals 3. Since we're talking about a distance, the negative one doesn't make a lot of sense. So x equals 3 is the only solution we get. Let's tangle with another one. We have two secants. So the theorem says the whole secant times the outside part equals the whole thing times the outside part. So the whole thing, x plus 6, times 6, which is the outside, equals the whole thing, 19, times the outside, which is 7. Okay. Distributing, we'll subtract the 36 over and then do a little division. And we get 16 and 1/6, which I made into a decimal there. Okay. So far, so good. We have one more situation to look at, and that's the one where you have a secant and a tangent intersecting. Okay. Now, part of this theorem works the same way. You'll get the whole secant times the outside part. With the tangent part up here, it's just the tangent part squared. All right, this is kind of a special case of the previous theorem. So it's the whole segment times the outside equals the tangent part squared. So let's hammer through one of these so that you see how that works. Okay. We have a secant, we have a tangent. So the whole length here, 2x plus 4, times the outside part, which is just x, equals the tangent part squared. Okay, if we distribute that, then we can subtract the 100 over. And now I'm going to make my life a little easier at least. Before I try to factor this, I'm going to see there's something in common. So I'm going to divide everything by 2. Makes my numbers smaller. So now I need factors of 50 that subtract to make 2. And there's not any. Oh no, whatever shall we do? We'll go to our old friend, the quadratic formula. Okay, we learned how to deal with this in Algebra 1. You've used it a few times here in geometry this year. You'll use it some more in Algebra 2, for those of you that haven't taken that yet. So it should be our old dear friend. Okay. A in this case is 1, B is 2, and C is negative 50, so I'm going to plug the values in. Okay. Clean up the arithmetic. The square root of 204 is about 14.283 within rounding. Okay. Now negative 2 plus 14.283 and then divided by 2 gives me an answer of 6.142. Negative 2 minus that, then divided by 2 gives me a negative value. Again, we're talking about a side length, or a segment length, so the negative value doesn't make any sense. We'll stick with the positive answer. Okay. A quick way to check and make sure things are okay is to plug this back in. 6 and change makes that a little over 10. And makes that a little over 6. So this whole length is 16 and a quarter roughly. 16 and a quarter times 6.1. 16 times 6 is 96. That's pretty close to 100 already. And that's just doing it in my head. If I had a calculator handy, I could just plug those numbers in and get exact values, and I'd probably get like 9.98 or something like that. So that's a checkpoint. Make sure it works to see if you get 10. In this case, 10. Whatever you got out here, squared. So a lot of segment work. We got to break out the quadratic formula, which is always fun. If you had questions along the way, hopefully you wrote those down. Bring them in with you, and we'll see you in class.